Find somewhere comfortable tonight, wherever you are, lying down, curled up, somewhere quiet and dim. You don't need to follow any of this closely. You don't need to hold on to any particular thought or remember any particular fact. The words will simply arrive, the way distant sounds arrive through a window at night, and you can let them pass through you just as easily. We're going to travel somewhere tonight. Not far in the sense of effort, quite the opposite. We're going to drift back, very slowly, through time and space, through events so enormous and so ancient that they make the whole of human history feel like a single quiet afternoon. And somewhere in that journey, we'll find something you've been carrying with you your whole life, without knowing quite where it came from. If today was hard, you don't need to bring it with you. Whatever you're carrying from the last few hours, the last few days, you can set it down here at the edge of this. The universe has been patient for billions of years. It can hold whatever you need to put down. Just let your body go heavy. Let your eyes stay closed. The story will find you. We're in no hurry tonight. There is something worth sitting with before we begin. Something small and ordinary that contains a question so deep it took humanity most of its history to even ask it properly. Think of gold, not the idea of wealth, not the abstraction of value, just the physical thing, a ring on a finger, a chain resting against warm skin, the way it catches light and holds it for just a moment before giving it back. Gold has been with us for so long, found in riverbeds and mountains and the earth beneath our feet, that it can feel like it simply belongs here, like it grew here, like it is native to this world, the way rivers are native, the way stone is native. But it didn't grow here, it didn't form here. Not a single atom of gold on this entire planet was made on this planet. Every atom of gold you have ever seen or touched arrived here from somewhere else, from events so violent and so distant that if you tried to describe them in full to someone, they might not believe you. The gold in a wedding ring, in old coins kept in a drawer, in the circuitry of the phone you may have set down beside you tonight, all of it was forged in the depths of stars, scattered across space and carried to this world by ancient collisions long before the first human being drew breath. That is what we're going to explore tonight. Not quickly, not urgently. We're going to drift through it, the way you drift through a dream, catching images and ideas as they come, letting them settle somewhere quiet inside you. It begins at the very beginning, which is, in its own way, almost nothing at all. The universe, in its first moments, was extraordinarily simple. Not simple in the way a quiet room is simple. Simple in the way a blank page is simple, full of potential, but containing almost nothing yet written. The matter that existed in those first few minutes was not the rich, varied matter we know today, with its dozens and dozens of different kinds of atoms, each with its own character and weight and way of bonding with others. It was almost entirely just one thing: hydrogen. The lightest, most basic form of matter there is, a single tiny particle at the center, one equally tiny particle orbiting it. That is all. Alongside the hydrogen, there was helium, a little heavier, a little more complex, but still breathtakingly simple by any standard. And then, in quantities so small, they barely deserve a mention, a whisper of lithium, the third lightest element. That was it. That was the periodic table of the early universe. 3 entries. 3 entries. To understand why, it helps to picture what the universe was like in those first few minutes. Imagine something incomprehensibly hot. Not hot in the way an oven is hot, or even in the way the surface of the sun is hot. Hot in a way that makes those comparisons meaningless. A heat so extreme that matter and energy were barely distinguishable from each other, and the tiny particles that would eventually become atoms were flying around too fast and too furiously to settle into anything. In those first seconds, the universe was busy doing something remarkable. Protons and neutrons, The building blocks of every atomic nucleus that has ever existed were being assembled from even smaller ingredients. They were slamming into each other, sticking together, forming the seeds of what would eventually become atomic nuclei. And for a brief window, the conditions were just right for some of those protons and neutrons to fuse together, building the first nuclei. Hydrogen came first, because a single proton is all a hydrogen nucleus needs to be. Then helium, built from 2 protons and 2 neutrons bound together. But the universe was expanding. It had been expanding since the very first instant, and as it expanded it cooled the way air cools when it rushes out of a pressurized container. And the cooling happened fast, not gradually, not gently, but with an urgency that left no time for anything more complex to form. Within roughly the first 3 minutes, the temperature had dropped far enough that fusion simply stopped. The window closed. The universe had cooled past the point where protons and neutrons could be forced together, and whatever nuclei existed at that moment were the ones that would have to do. 3 elements: hydrogen, helium, and the faintest breath of lithium. Imagine the whole of chemistry, everything that makes up rocks and oceans and living cells and the air we breathe, and then imagine none of it yet existing, just those 3 light, simple things drifting in an enormous dark. There were no metals, no carbon, no oxygen, no iron, no calcium, no gold. The universe was vast, and it was dark, and it was, in terms of chemical richness, almost entirely empty. And yet, there is something beautiful in that emptiness, if you sit with it long enough, because that hydrogen and helium weren't inert. They weren't finished. They were, in the most patient way imaginable, waiting, drifting in great slow clouds through the dark, pulled gently by gravity toward one another over hundreds of millions of years, gathering and thickening and warming in their centers until something remarkable began to happen. The universe was preparing to make stars. And stars, it turns out, are the most extraordinary factories that nature has ever devised, not because they work quickly, quite the opposite. They work with a patience that makes geological time feel brief, and in doing so they transform the simplest matter in existence into something far richer, far stranger, far more beautiful. That transformation is where our story really begins, and it begins, as so many deep things do, with fire. A star is, at its heart, a kind of fire, but not fire the way we usually think of it. Not the combustion of wood or gas where molecules react with oxygen and release heat and light. A star's fire is something older and more fundamental than that. It is the fire of nuclei pressing against each other under such extreme pressure and heat that they merge. Fusion, the joining of atomic hearts. When a cloud of hydrogen gas collapses under its own gravity and the pressure at the center becomes great enough, hydrogen nuclei begin to fuse into helium. And in that fusion, a tiny fraction of the matter involved is converted directly into energy, into light and heat that push outward against the inward pull of gravity. The star finds a balance. It neither collapses further nor flies apart. It simply burns steadily for an almost incomprehensible length of time. Our own sun has been doing this for about 4.5 billion years. It will continue for roughly another 5 billion. The scale of that patience is worth letting settle somewhere in you. Every morning that has ever existed on this planet, every sunrise that any human or animal or ancient creature has ever witnessed, has been powered by that same slow, steady fire. But hydrogen doesn't last forever, even in a star as patient as the sun. Eventually, after millions or billions of years, depending on the star's size, the hydrogen at the core begins to run low. And here is where the star faces a choice, though choice is perhaps too deliberate a word. It faces a consequence. The outward push weakens, gravity gains the upper hand, the core contracts and heats further, and a new threshold is crossed. The temperature becomes high enough to fuse helium. Helium nuclei, fusing together, produce carbon. Then, with more heat and pressure, carbon can fuse into heavier things still. Oxygen, neon, magnesium. Silicon. Each time one fuel runs low, the star contracts a little further, heats a little more, and unlocks the next door. It is like a fire that keeps needing bigger and bigger logs to keep burning, and for a while, the universe keeps providing them. This is the deep story of where most of the atoms in our world come from. The carbon in every living cell on Earth was made inside a star. The oxygen you are breathing right now was forged in stellar cores. The silicon in sand, in rock, in the chips inside every electronic device. All of it made in that slow, layered process of fusion, one element building toward the next. There is a group of people who deserve to be remembered here in the quiet of this night. 4 astronomers working in the 1950s who took what had been a scattered collection of ideas and observations and wove them into something coherent and lasting. Their names were Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. In 1957, they published a paper, a long, meticulous, deeply considered paper that laid out for the first time a complete picture of how stars build the elements. It was, in its own quiet way, one of the most profound things ever written, because what it said, in careful scientific language, was this: the stuff you are made of was made in stars. The atoms of your body were forged in nuclear fires billions of years ago, inside stars that lived and died long before our sun was born. You are not separate from the cosmos, you are assembled from it. Fred Hoyle had actually been circling this idea since 1946, when he first proposed that nuclear reactions inside stars could account for the heavier elements. But the 1957 paper, which became known simply by the initials of its 4 authors, was the full flowering of that idea, supported by extensive astronomical observation and laboratory measurement. It was a quiet revolution, not the kind that announces itself with noise and urgency, but the kind that simply changes everything, gradually, the way a tide changes a shoreline. William Fowler received the Nobel Prize in Physics in 1983 for his work in this area, a recognition that arrived more than a quarter century after the paper that deserved it. Margaret Burbidge, who contributed enormously to the work, was not included in that recognition, a fact that has since been widely noted with something between regret and quiet anger. History has a way of taking its time with justice. But the science endures, regardless of how its credit was distributed, and what the science tells us is that stars are not merely sources of light and warmth, they are ancient, patient workshops, spending their long lives converting the simple raw materials of the early universe into something more complex, more varied, more interesting. And yet, there is a wall. A place where even the most massive, most patient star eventually runs out of road. A place where the long sequence of fusions comes to an end, not because the star runs out of material, but because the material stops cooperating. That place is iron. Iron is where the fire goes out, and understanding why requires us to look a little more carefully at what fusion actually is and why it can't go on forever. The energy released in fusion comes from a kind of accounting trick that nature performs. When 2 lighter nuclei fuse into a heavier one, the resulting nucleus is very slightly lighter than the sum of its parts. A tiny amount of mass has been converted into energy. That is the fire. But as nuclei get heavier and heavier, the accounting changes. The savings get smaller, and at iron, they disappear entirely. Iron sits at a kind of low point in nature's ledger, a place where neither fusion nor the reverse process releases any energy at all. Iron is, in a sense, the most stable thing a nucleus can be. It is matter at rest. For a star, this is catastrophic, and the chapter of what happens next is one of the most extraordinary in all of nature. But we'll arrive there in good time. For now, let the image of those 4 astronomers sit with you. 4 people in the mid-20th century, working with telescopes and notebooks and careful thought, who looked up at the night sky and understood for the first time that every star is a forge. Every star is, in its own slow way, making the world. Before we reach the violence of iron and collapse and explosion, there is a gentler story to tell. A quieter kind of alchemy that takes place not in the roaring heart of a star, but in its outer layers, in the long, slow twilight of its later years. Some stars, as they age, swell into vast, cool, reddish things, enormous and unhurried, their outer layers puffed out to hundreds of times their original size. The kind of star that, if placed at the center of our solar system, would swallow several of the inner planets whole. These swollen ancient stars are in the final chapters of their lives, and in those chapters something quiet and remarkable is happening in certain regions of their interiors. Free neutrons, neutrons that are not bound inside any nucleus, just drifting, are being produced in small numbers by reactions happening deep inside, and those free neutrons are doing something patient and methodical. They are drifting into the nuclei of atoms and being absorbed, one at a time. Slowly, with what might as well be called deliberateness, if deliberateness could exist on an atomic scale. Here is what that means in plain terms. An atomic nucleus is a cluster of protons and neutrons held together at the center of an atom. The number of protons determines what element it is. Iron always has 26 protons, gold always has 79, and so on. But the number of neutrons can vary. A nucleus can absorb an extra neutron and become a heavier version of the same element, still the same element, but carrying a little more weight. Sometimes, when a nucleus has absorbed enough extra neutrons, it becomes unstable. It can't hold that configuration together indefinitely, and so, over time, one of its neutrons quietly transforms. It sheds a tiny particle and becomes a proton instead. When that happens, the nucleus gains a proton, and in gaining a proton, it becomes a different element. It has stepped up the ladder, become something new, without any explosion, without any drama, just a quiet internal rearrangement, like a building shifting its foundations in the night. This process, neutrons drifting in one at a time, long pauses in between, unstable nuclei gently rearranging themselves, is called the slow neutron capture process. The word capture just means the nucleus absorbs the neutron, takes it in. And it is slow because the neutrons arrive infrequently enough that the nucleus has time to rearrange before the next one comes. Think of it like a craftsman adding beads to a necklace, one at a time, with long pauses between each addition to check the work. Each new bead added, each quiet rearrangement produces something slightly different from what was there before. Over thousands of years, inside these vast, patient, aging stars, this process builds elements that could never be produced in the younger, hotter phase of a star's life. Strontium, barium, lead. These are among the elements that this slow, gentle process is responsible for. Roughly half of all the elements heavier than iron that exist in the universe were made this way. Not in explosions, not in catastrophe, but in the quiet interior of old stars over enormous stretches of time. There is something deeply comforting about that, if you let yourself feel it. Not all creation requires violence. Some of the most important building in the universe happens slowly, patiently, one small addition at a time. The slow process has limits, though. It can only build so far up the ladder of elements before it runs out of road. Lead, for instance, is near the top of what it can reach. Above a certain point, the nuclei it would need to create are so unstable that they fall apart almost as fast as they form. The slow process, patient as it is, cannot push past that barrier. For the heaviest elements, for gold, for platinum, for uranium, something more extreme is needed. Something that doesn't wait for a nucleus to rearrange itself between neutron arrivals. Something that floods a nucleus with so many neutrons so fast that stability becomes irrelevant, at least for a moment. That something requires a kind of event that makes even the death of an ordinary star seem gentle. Inside those swollen ancient stars, the slow process runs its long course, and the star eventually sheds its outer layers into space in a gentle, expanding cloud, a beautiful, glowing shell of enriched gas drifting outward through the galaxy, carrying its strontium and barium and lead back into the wider universe. The core that remains is a small, dense, quietly fading ember. And somewhere in that expelled cloud, those carefully made atoms drift free, mixing with the gas between the stars, waiting to be gathered up again into new nebulae, new stars, perhaps new planets. The necklace of matter, patiently assembled over millennia, released back into the dark. But the story of the heaviest elements is still ahead of us. It requires a different kind of star entirely, a larger one, a more extreme one that doesn't end with a gentle exhalation of enriched gas, but with something that briefly outshines entire galaxies. Let us spend some time with iron. Not the iron of tools or cookware, or the deep red color it gives to blood. The iron of physics, the iron of nuclear structure, the iron that sits at the bottom of an energy valley so deep that the universe itself cannot dig further without giving something up. To understand what iron means to a star, it helps to think about energy in a particular way. Every atomic nucleus, depending on how many protons and neutrons it contains, has a certain amount of energy locked up in the bonds holding it together. When you fuse two lighter nuclei into a heavier one, the result is often a nucleus whose bonds are more efficient. It holds itself together with less total energy than the two separate pieces had. As you move up through the elements, from hydrogen to helium to carbon and beyond, each step releases a little less energy than the last. The gains are getting smaller. The universe is, in a sense, running out of profit in the fusion business. And then you reach iron, and the profit disappears entirely. Iron's nucleus is so efficiently assembled, its bonds so well organized, that fusing it with anything else doesn't release energy. It requires it. You have to put energy in to make iron fuse into something heavier. And a star has no external source of energy to draw on. It only has what fusion gives back. So when a massive star, far larger than our sun, has been burning through its sequence of fuels for millions of years, and the core finally begins to fill with iron, something very quiet and very final happens. 2. Fire goes out, not everywhere at once, not in the outer layers which are still burning their own fuels. But at the center, where the iron accumulates, there is nothing left to ignite. The iron simply sits there growing, as more iron rains down from the layers above. Picture a massive star in its final hours. It is enormous, perhaps 20 or 30 times the mass of our sun, its outer layers so vast that they stretch across a distance it would take light years to cross. And yet those outer layers are, in a sense, irrelevant to the crisis unfolding at the center. The star is structured in shells, like an onion, each layer burning a different fuel. The outermost shell is still fusing hydrogen. Inside that, helium. Inside that, carbon. Then neon, then oxygen, then silicon. And at the very center, the iron core, growing slowly heavier, growing slowly denser, held up by nothing more than the resistance of the particles inside it to being pressed any closer together. That resistance is real. Particles have a kind of stubbornness, a refusal written into the laws of physics to occupy the same space at the same time. For a while, that stubbornness is enough to hold the iron core up against gravity's pull. But as the core grows heavier, gravity grows stronger, and the resistance has a limit. The star stands on the edge of something. It has been standing on this edge, in a sense, for its entire life. The balance between fusion's outward push and gravity's inward pull. But now, for the first time, the push is gone. Only the pull remains. And the star waits. Not consciously, not with any awareness, but in the language of physics there is a threshold that has not yet been crossed, a final moment of equilibrium before the balance tips. The iron core sits at the center of this enormous ancient structure, surrounded by the products of billions of years of fusion, all the carbon and oxygen and silicon and sulfur that the star has spent its life making, layer upon layer, a geological record of cosmic chemistry written in light and heat. Outside, in space, nothing looks unusual. The star shines. It has been shining for millions of years, and from a distance it looks no different now than it did 1,000 years ago. The drama is entirely interior, entirely invisible. But the threshold is very close now. The iron core is approaching the point where even the stubbornness of its particles cannot hold. When it crosses that point, everything that has been building for millions of years will be released in a fraction of a second. And in that extreme environment, the rarest and most precious elements in existence will be born. The collapse, when it comes, is almost instantaneous. The iron core, which has been growing for years, crosses its threshold and falls. Not slowly, not gradually. It falls at 1/4 of the speed of light, the entire core shrinking from something the size of the Earth to something the size of a city in less than a second. The particles that have been resisting compression are suddenly overwhelmed by gravity so extreme that they are forced to merge. Protons and the tiny orbiting particles around them are crushed together, and the whole core becomes a dense, extraordinary object made almost entirely of neutrons, packed together as tightly as matter can be packed. And then it bounces. The newly formed neutron core is so incomprehensibly dense that even the infalling material of the star cannot compress it further. The collapse reverses in an instant, sending a shockwave outward through the star at speeds that make any earthly comparison meaningless. That shockwave tears through the outer layers of the star and, within seconds to hours depending on the star's structure, blows them apart entirely. A supernova. One of the most energetic events in the universe. The light from a supernova can briefly outshine the entire galaxy it lives in. Hundreds of billions of stars, all their combined light outshone by a single dying one. If a supernova occurred in our own galaxy close enough to see clearly, it would be visible in daylight. It would cast shadows at night. It is, in every sense, an extraordinary thing. But what matters most for our story happens not in the light, not in the visible explosion, but in the environment created in those first chaotic seconds. Because in the collapse and the bounce and the shockwave, conditions arise that exist nowhere else in the universe under ordinary circumstances. Temperatures beyond anything that can be produced in a laboratory. And neutrons, vast floods of free neutrons, liberated by the crushing of the core, streaming outward through the surrounding material. Those neutrons encounter atomic nuclei, and what happens next is the opposite of the slow, patient process we explored earlier. Instead of one neutron arriving and being absorbed, with time for the nucleus to rearrange before the next one comes, the neutrons arrive in an overwhelming flood. A nucleus might absorb 10, 20, 30 neutrons in rapid succession, far faster than it has any chance to shed them. It is driven far from anything resembling stability. It becomes a wildly neutron-rich, deeply unstable thing, a nucleus that could not exist under any ordinary circumstances. Think of it this way. The slow process is like someone carefully loading a boat, one item at a time, allowing the boat to settle between each addition. The rapid process is like an ocean wave crashing over that boat and filling it with water all at once. The boat is overwhelmed, taken somewhere it never would have gone under its own navigation. These wildly overloaded nuclei don't stay in that state forever. After the initial neutron flood passes, and it passes in seconds, they begin the long, slow process of finding their way back to stability. Neutrons transform into protons, one at a time, over days and weeks. A nucleus that absorbed 20 extra neutrons and became a bloated, unstable version of one element slowly decays, step by step, into something entirely new, something heavier, something that didn't exist before. Gold is born this way. Platinum, uranium, the heaviest, rarest elements in the periodic table, the ones that required more than any ordinary stellar process could provide, are the products of this rapid neutron flood, this brief and violent immersion in conditions that exist nowhere else. The image that stays with me is this. Imagine a nucleus being picked up by a wave and carried far out into rough, deep water, far from the shore of stability, far from anything it recognizes. It is carried out there in seconds. And then the wave recedes and the nucleus begins the long, quiet journey back to shore. But the shore it reaches is not the one it left. It has been changed by the journey. It comes to rest somewhere new, as something new, and that new thing is stable, and it will persist for billions of years. After the supernova, the material ejected by the explosion drifts outward into space, a slowly expanding cloud of gas and dust, enriched with all the elements the star made in its life, and all the heavy elements made in its death. Gold and platinum and uranium, mixed in with iron and silicon and oxygen, scattered across the galaxy on the winds of the explosion. That cloud will cool and thin over thousands of years. Some of it will drift into existing nebulae and mix with their gas. Some of it will eventually be gathered by gravity into new clouds, new collapsing regions, new stars and new planets. And some of it, after billions of years of wandering, will find its way into a rocky world orbiting a middle-aged star in an unremarkable corner of the galaxy. Some of it will, eventually, be worn on a finger or rest in a drawer or lie quietly in the dark beside someone who is drifting towards sleep. But not all of the universe's gold comes from supernovae. There is another source, arguably even more extreme, even more prolific. And it involves not the death of one star, but the meeting of two dead ones. When a massive star explodes as a supernova, it doesn't always destroy itself entirely. Sometimes, what remains at the center after the explosion is that extraordinarily dense neutron core, the city-sized object made almost entirely of neutrons, packed so tightly that a single teaspoon of its material would weigh as much as a mountain. These objects are called neutron stars, and they are among the strangest things in the known universe. They spin, often extremely fast, some of them rotating hundreds of times per second, sweeping beams of radiation through space like cosmic lighthouses. They are hot, incredibly hot at first, though they cool over millions of years. They are small, perhaps 20 kilometers across, less than the distance across a large city, but their gravity is immense and their density is something the human mind genuinely cannot picture without assistance. Sometimes, two massive stars in the same region of space both explode as supernovae and both leave neutron stars behind. And sometimes those two neutron stars are close enough and moving in just the right way that gravity binds them to each other. They orbit one another. Not quickly at first. Their orbits can be vast, taking hours to complete a single circuit. But as they orbit, they lose energy very slowly in a form that we'll come to in a moment, and their orbits gradually decay. Over hundreds of millions of years, they spiral slowly inward, drawing closer and closer to each other, until eventually, the collision of two neutron stars is one of the most violent events that can occur in the present universe. Two objects of almost incomprehensible density, each containing more mass than our Sun, colliding at a significant fraction of the speed of light. The merger releases more energy in a fraction of a second than our Sun will release in its entire 10 billion year lifetime. And in that merger, the conditions for the rapid neutron capture process are met in a way that may surpass even what happens in a supernova. The neutron-rich material of both stars is flung outward in all directions, and in that ejected material, the same overwhelming neutron flood occurs. Nuclei bombarded faster than they can respond, driven far from stability, then slowly finding their way back as something heavier and new. We know this not just from theory, but from direct observation. On the 17th of August 2017, something remarkable happened. Or rather, something that had been happening for hundreds of millions of years finally reached us. Two neutron stars, having spiraled toward each other across an almost incomprehensible span of time, finally merged in a galaxy about 130 million light-years away. The merger sent a ripple through space itself, not a wave of light, not a wave of sound, but a wave in the fabric of space and time, a gravitational wave, a gentle stretching and squeezing of space that propagated outward from the collision at the speed of light. It arrived at Earth on that August morning and was detected by two extraordinarily sensitive instruments, one in Louisiana, one in Washington State, that can measure a change in distance smaller than a fraction of the width of a proton. The detection of that signal was itself extraordinary, but what happened in the hours and days that followed was perhaps even more so. Telescopes around the world and in orbit were turned toward the location of the signal, and there, in a galaxy called NGC 4993, a glow appeared, a new fading light. A kilonova, as it is called, the afterglow of the collision, shining with the light of newly made heavy elements. Astronomers studied that glow carefully. They analyzed its color and brightness as it faded over the following days, and what they found confirmed what theory had long predicted. Gold and platinum were being made right there in real time in that fading light. It was the first time in human history that the creation of gold had been directly observed. Subsequent research deepened the picture. A study published in 2021 by researchers at MIT and the University of New Hampshire compared the output of neutron star mergers with other possible sources of heavy elements. Their findings were striking. Over the last 2.5 billion years, collisions between two neutron stars likely produced somewhere between 2 and 100 times more heavy metals than any other known type of event. The range is large because these things are genuinely difficult to measure, but even at the low end, the implication is clear. Neutron star mergers are the universe's primary gold mines. Think about what that means. The gold in a ring, in a coin, in the circuitry of a machine. Much of it traces its origin not to a single exploding star, but to a collision between two dead stars that had been slowly spiraling toward each other for hundreds of millions of years. A meeting that was set in motion long before our sun was born, finally completing itself in a flash of light that took another 100 million years to reach us. The universe keeps its appointments. It just keeps them on its own timescale. For a while, it seemed like the picture was becoming clear. Ordinary stars make the lighter elements. The slow process in aging stars makes elements like barium and lead, and collisions between neutron stars make the heavy elements. Gold, platinum, uranium, a tidy sequence. But the universe, it turns out, had been keeping something else quiet. In April of 2025, a paper was published that rearranged part of the timeline in a way that surprised even the researchers involved. A doctoral student at Columbia University named Anirudh Patel, working with a team of colleagues, had gone back to look at archival data from NASA and European Space Agency telescopes, data that had been sitting in databases for 20 years, waiting for someone to ask the right question of it. What they found concerned a particular kind of neutron star called a magnetar. A magnetar is a neutron star with a magnetic field of almost incomprehensible strength. If you could somehow place a magnetar where our moon is, its magnetic field would be strong enough to erase the information on every credit card on Earth from that distance. Strong enough to disrupt the iron in your blood from hundreds of thousands of kilometers away. The magnetic fields of magnetars are the strongest known in the universe, and they make even ordinary neutron stars, which are already extreme by any measure, seem almost mild by comparison. Magnetars are prone to something called a giant flare. Occasionally, the enormous stored energy in a magnetar's magnetic field is released in a sudden, brief outburst, a flash of energy so intense that it can be detected across the galaxy, and in some cases across neighboring galaxies. These flares last only a fraction of a second to a few seconds. They are among the brightest events that can be observed in the universe. What Patel and his colleagues found was evidence in that old telescope data that giant magnetar flares may do something that nobody had fully appreciated before. They may scatter heavy elements into space. The physical mechanism is still being worked out. The exact details of how the energy of the flare interacts with the neutron-rich material of the magnetar's surface or interior to produce and eject heavy nuclei is an open question, one that researchers are actively exploring. The team estimated that giant flares from magnetars could account for as much as 10% of all the heavy elements heavier than iron in our galaxy. 10% is not the majority. Neutron star mergers still appear to be the dominant source, but 10% of all the gold in the Milky Way is an enormous amount of material. More importantly, the timing changes everything. Neutron star mergers require two massive stars to be born. Both live out their lives, both explode as supernovae, both leave neutron stars behind, and then those two neutron stars must spiral together over hundreds of millions of years. That whole process takes a very long time. In the early universe, when galaxies were young and stars were just beginning to live and die for the first time, there simply hadn't been enough time for many neutron star mergers to occur. And yet, when astronomers look at the oldest stars in our galaxy, stars so ancient they were already old when our sun was born, they find heavy elements in their atmospheres. Elements that, according to the neutron star merger timeline, shouldn't have been there yet. The universe was apparently enriched with gold earlier than the merger model alone can explain. Magnetar flares could fill that gap. Because magnetars can form quickly, a massive star can be born, live its brief life, and leave a magnetar behind in just a few million years, and a magnetar can flare early in its life. The timescale is far shorter than the long spiral of two neutron stars finding each other. If magnetar flares were seeding the early universe with heavy elements, that would explain the gold in those ancient stars, gold that appeared before the universe's first neutron star mergers had had time to occur. It is a finding that quietly deepens the story, not replacing what came before, but adding an earlier chapter to it. The universe, it seems, found a way to begin making gold even before it had assembled its most powerful forges. Alongside this discovery, the tools for understanding these processes are themselves becoming more sophisticated. In 2026, an international team developed an artificial intelligence system to model the nuclear reactions involved in the rapid neutron capture process during neutron star mergers. The challenge they were addressing is genuinely extraordinary. The complete pathway from the initial neutron flood to the final stable elements involves thousands of individual steps, passing through hundreds of short-lived unstable nuclei that are so exotic they have never been observed in a laboratory and may never be. Mapping that pathway requires tracking each step, accounting for every possible branch and outcome. The AI system, published in a physics journal in the summer of 2026, could navigate that complexity far more efficiently than previous methods, opening the possibility of better predictions and a stronger connection between what telescopes observe in kilonovae and what experiments on Earth can test. It is the kind of tool that doesn't change what the universe does, but helps us read it more clearly. And still, questions remain. The role of nuclear fission in these extreme events, the question of whether some of the heaviest nuclei, having been built up by the neutron flood, then split apart into lighter ones and contribute to the final element, mix in a more complex way, is an area of active research. A team in Sweden, funded through a major research foundation, has been working specifically on understanding fission's role in neutron star collisions, trying to untangle how the splitting of heavy nuclei feeds back into the whole process. The picture is not finished. It may never be entirely finished. The universe is under no obligation to be simple, and the processes that make gold are, appropriately enough, among the most complex that nature has ever produced. But the outline is clear, and it is beautiful, and it is, if you hold it gently and don't press it for more precision than it yet has, a complete enough story to carry with you. The universe has been making gold since very early in its history. It makes it in the deaths of massive stars. It makes it in the collisions of neutron star pairs that have been slowly finding each other across hundreds of millions of years. And it made it, perhaps first of all, in the brief, brilliant flares of magnetars in the young galaxies of the early universe, when everything was new and the first heavy elements were just beginning to find their way into the world. And all of it eventually found its way here. There is a question worth arriving at slowly, here at the end of all this. Not a question with a sharp edge, not a puzzle to be solved. More like a door that has been standing open for the whole of this journey, and we have simply been walking toward it. What does it mean that you are made of this? Not metaphorically, not as a poetic gesture toward connection and meaning, though it is that too. Literally, in the most precise physical sense, the atoms that make up your body were forged in stellar fires and stellar deaths and stellar collisions across billions of years and billions of light years. They were scattered into space, gathered by gravity, incorporated into clouds, into new stars, into the disk of gas and dust that eventually became our solar system. They fell together with everything else that makes up this small, warm, improbable planet. They were assembled over billions more years into the chemistry of life, into cells and proteins and the long, slow architecture of living things, until eventually they arrived here, in this particular arrangement, breathing softly in the dark. The iron in your blood, every molecule of hemoglobin carrying oxygen through your body right now, contains iron atoms that were fused in the core of a star that died before our sun was born. That star lived for millions of years and ended in an explosion, and the iron it made drifted through space and eventually became part of the cloud that formed our solar system, and eventually became part of the ground, and eventually became part of the food, and eventually became part of you. The calcium in your bones was made the same way. The oxygen you are breathing, the carbon that forms the backbone of every biological molecule in your body, all of it came from stars. And the gold, if you are wearing any, or if there is any nearby, in a drawer or on a shelf or somewhere in the room, that gold has an even stranger history. It was not made in the core of an ordinary star. It was made in a moment of extreme violence, in the rapid neutron flood of a supernova or a neutron star collision, in conditions that lasted seconds and produced something that will last essentially forever. It drifted through space, perhaps for billions of years. It arrived on early Earth carried by asteroids and meteorites, those ancient wanderers that bombarded the young planet before its surface had fully cooled. It sank into the ground, was lifted by geological processes, was found by human hands perhaps thousands of years ago, was shaped and passed down and worn and kept, and eventually came to rest wherever it rests tonight. Every piece of gold on Earth has that history, every single atom of it. There is something in that fact that is difficult to name, but feels important in the quiet of a night like this. The rarest, most beautiful things are not made in calm. They are made in the most extreme conditions the universe can produce, in the collapse of iron cores, in the collision of neutron stars, in the magnetic flares of extraordinary objects in young galaxies. They are made in violence and chaos and temperatures that make the surface of the sun feel mild. And then they drift, they cool. They travel across unimaginable distances and unimaginable spans of time, and they arrive here, quiet and heavy and warm, held in hands that have no idea where they came from. If all the gold ever mined by human beings in all of history were gathered together in one place, it would fill roughly 2 large swimming pools. That is all. After thousands of years of mining, on every continent, in every civilization, 2 swimming pools. The rarity of gold on Earth is a direct reflection of how difficult and how extreme the conditions are that make it. It is rare because the universe doesn't produce it easily. It is rare because it requires the death of stars, the meeting of their dense remnants, the brief, impossible physics of those moments of collision. And yet here it is. here you are. The calcium in your bones is ancient, forged in a star that died billions of years ago. The iron in your blood has traveled further than any human journey. The carbon in your cells has been part of stars, part of interstellar clouds, part of ancient oceans, part of creatures that lived and died long before anything resembling a human walked the earth. You are not simply connected to the universe, you are assembled from it. You are what the universe looks like when it has been working on something for 13 billion years. There is a strange and quiet comfort in that, if you let it in. Whatever feels heavy tonight, whatever worry or sadness or tiredness you brought with you to this moment, it is being carried by a body made of the oldest and most well-traveled matter in existence. The atoms of you have survived supernovae. They have drifted through the cold between the stars. They have been part of the unimaginable chaos of neutron stars colliding, and they have come through it, patient and unchanged, and here they are, arranged into something that breathes and thinks and wonders. The universe spent billions of years making you possible, not you specifically. The universe doesn't plan, doesn't intend, doesn't direct, but it built slowly and through extraordinary events the conditions and the elements and the chemistry that allowed something like you to exist. And here you are, at the end of that long journey, lying quietly in the dark, thinking about gold. Let your body feel heavy now. Let all that ancient matter rest. The iron in your blood has been through things that would make the hardest day feel brief. The calcium in your bones has traveled distances that make any distance you have ever covered seem like a single step. You are made of patient, ancient, extraordinary stuff. Matter that has been through the worst the universe can offer and come out the other side as something warm and alive and here. Outside, somewhere, the stars are doing what they have always done, burning slowly, building patiently. Some of them in their final hours, some of them just beginning. The universe is still making gold, somewhere, right now, in a collision or a collapse that we may not observe for another 100 million years, or that we may detect tomorrow as a faint ripple in space reaching our instruments after a journey across the cosmos. It doesn't stop. The universe doesn't rest, but you can. You have been made from the most extreme processes in existence, and you have arrived here in this quiet, in this dark, in this particular moment of stillness. Drift now, if you're ready. Sleep well.